just x? No, right? And isn't adding 1 to that make this even bigger? So this is not possible. This is not true, so I can't handle that. I cannot handle this expression. So I can't use the negative case. I can only use the positive case. I hope that makes sense. So I just wanted you to see that these formulas, again, these weren't found under some, ancient rock. Yeah, I don't want to get, there's no like tablets of math formulas that we found, luckily. I mean, each one of these we had to derive, and the derivation of these things is complicated sometimes. So I'll let you, you could do the cosine hyperbolic on your own, the inverse one, but not required. So we just showed that that was true. Now, assuming that we know these, so let's just assume now that we have these definitions, we don't need to prove them. Let's go ahead and move on to example 4. Let's take the derivative of cosine hyperbolic of x. Cosine hyperbolic inverse. I forgot to say inverse. So what is the derivative of cosine hyperbolic inverse of x? Well, we have to know what cosine hyperbolic inverse is, right? What is this? Well, scroll up a little bit here. It's natural log of x plus the square root x squared minus 1, right? So I'm taking the derivative of this. Right? I'm just going to take the derivative of that. So just use chain rule, right? What is the derivative of the natural log of something? 1 over it, right? So 1 over the x plus square root x squared minus 1. Then chain rule times the derivative of what's inside the natural log. So there's 2 terms, right? Derivative of x is 1. So I need this in parentheses, 1. Plus, now what's the derivative of the square root of x squared minus 1? So that's chain rule again, right? So 1 over 2 root x squared minus 1 times derivative of what's in there, 2x. Is that all? Is that it for that? So does everyone agree that's the derivative? Any questions on any piece of that? Let's clean it up because I want to show, look what I'm trying to show. I'm trying to show that that's equal to 1 over the square root of x squared minus 1. So do we have this now? 1 over, see, x plus root x squared minus 1 times, let's see, these 2's will cancel. 1 plus 1.
What's that second part of it?
Which one?
I'm sorry. Yeah, that part. Because I understand the first part of it.
Okay.
The second part is the one plus. Where'd you get that little section?
Okay, so remember we had natural log of this out here?
Yeah.
Okay, so first of all, derivative natural log of something is 1 over that something,
Yeah.
okay? Then we go inside here, so forget the natural log.
Oh, yeah, okay.
And then we have the 1 right there. And then this one is chain rule. You good? Thank you for asking, Nolan. Nolan? Yes, that's how I say it?
Yes, sir.
All right. All right, so just all I did was cancel the 2's here, so I haven't done much of anything. So how would you like to try and clean this up? Because I need to show it's equal to just 1 over the square root of x squared minus 1. Any suggestions on how to?
You put that one on the right together.
You mean like put these common denominator?
Yeah.
You could do that. You want to do that?
You know, these 2 roots.
Doesn't matter. I mean, this is algebra at this point. We just need to make it look like that. You want to try it? All right. I'll take the first suggestion if that's what we're going to get. All right, so when you get a common denominator there, it's going to look like this. Right? So all I did was turn this into a fraction. It was that root over that root again, right? Just a 1. And then I put these two together and got this. You're there. Do y'all see it? Do you see it? This is this now. And they cancel. So, good move. That worked. That equals, the only thing left, 1 over square root x squared minus 1. So I only gave you 3 of the definitions, right, for the inverse hyperbolic trig functions. I only showed you 1 of the derivatives, but they're all in the book. And on the formula sheets, may I borrow yours for a second? Let's see if they're on there or not. Yes. The derivatives of all 6 inverse hyperbolic trig functions are on your formula sheet. What, the... Oh, the summary of it? Yes, but remember, is it the same?
Yeah, it
Is it this one? Reference page 5? Okay, yeah, but this is online, right? This is in our course under file, or I think it's under files. That's the official what you can bring to the test, which is the same.
It's identical.
As long as it's identical, we're good. What I don't want is someone bringing like their favorite formula sheet from pre-cal, because I can't give you something that your classmates don't have. So everyone's going to have the same formula sheets for the test. All right. And we continue here. We're actually at the end, the catenary, the hanging wire. So all this was to show you was that if you take a hyperbolic cosine function that looks like that, a cosine hyperbolic of x over a plus c, that when you graph that, that models a hanging wire. And so what I'd like to do now is do some problems from the book. And I've added, I think if you have these notes, I've added what's in yellow there is new problems that weren't in your notes. So that's your homework assignment for this section. Can everyone see that? I'm going to get a couple of these going. I'm not doing those problems. I'm going to do something similar to it. What if you're asked to find part A, cosine hyperbolic of 3, and then for part B, what is cosine hyperbolic of natural log 3?
Do you want us to start on 25 or 27? 26, 26, or do you want us to do
I don't know why I did that. Let me see. Yeah, I meant start at 27. But I mean, there's nothing stopping you from doing number 26 too. So. Remember, I'm not collecting homework, right? This is grown-up math, right? I shouldn't have to babysit you. And all the class from last semester told you should do your homework. So at this point, if you don't do it, well, we'll see how it goes for you, right? Cosine hyperbolic of 3. So all this wants is for you to evaluate it. Get your calculator out and do it. Now, the easiest way to do it is to rewrite using the definition, right? It's e to the x, but x here for us is 3, and then plus e to the negative 3, and then over 2, I'm just going to say times 1/2. So you get on your calculator and you do e cubed, and then you do plus e to the negative 3, and you figure out what that is, and you take half of it, and you get some decimal answer. Done? That's it. I'm not going to finish it. I just don't want you to look at that and be like, what am I supposed to do? All you're supposed to do is evaluate the function at 3. Now let's evaluate it at natural log 3. This will be the same exact thing, except instead of e to the 3, it's e to the natural log 3 plus e to the negative natural log 3, right? Times a half. What is e to the natural log 3? 3, isn't it? And I'm very curious for you to tell me what e to the negative natural log 3 is. It's not negative 3. It's unreal. Okay, are we all good with the fact that this is 3? Yes? Okay. 1/3. Good. That's what it is. How'd you do that?
I don't know. It was negative. I just kind of put it over. You put like the negative, it puts it in the denominator, right?
I think what you mean, hopefully, is this. You have a rule with logs that if you have a number out front, which this is a -1, that you can pop it up as an exponent, or that exponents pop out. It's this property. Natural log of x to the n equals n natural log x. Right? Powers come out as numbers, scalars in front, or scalars go up as powers. Right? So what I could do is I could take this -1 in front of the natural log. I can push this up and make it 3 to the -1. And then e and natural log kill each other off, and you're left with 3 to the -1, which is 1/3. Right? 3 to the -1 is 1/3. So this right here should be plus 1/3. And then times a half. See it? I don't know if that's what you were referring to, but that's the correct way. Questions on that? All right, the next, so what I did is kind of similar to like numbers 1 and 3. Problems 7, 9, 11, 15. Those are all verifying identities. Start with one side, turn it into the other. Start with, and have fun with those. Then 26 through 41, those are all derivatives. So it's just applying the rules, chain rule, and practicing with that. 47 and 48 are a little more interesting. So I think what I'd like to do is talk about 47. I'm going to do an adaptation of number 47. So let's say that we have two telephone poles that are 20 meters apart. And we have a wire that's hanging between these poles, right, connected to the poles. And that the graph of that wire is modeled by cosine hyperbolic x over 20 minus 10. So this is a catenary. All right, it's this picture we started class with. It's not a parabola. And the question I'm going to ask you is to try and find, like this wire comes into the pole, right? Like if I imagine running a tangent line here, then as I come into the pole, there's some angle that that wire makes with the pole. Yes? What is it? That's the question. So find, this will be part A, find the angle between the pole and the wire. Do y'all see what's being asked? It's on this side, if you imagine just like drawing kind of right there where they meet, you can imagine there's almost like a straight line, and we're trying to find this angle right here, which should be the same as this one, right? If the poles are the same height, then the angles should be the same on both sides. So it's really kind of up to us to determine which side we want to work with. So there's a few things that we have to assume here. The lowest point, okay, the lowest point on the catenary is going to be corresponding to our graph. It should be where x is 0. So this should be the y-axis right here. Now let's just verify that. If x is 0, right, if x is 0, then what would we get? Cosine hyperbolic of 0, which is, well, do we know? Well, we could find it pretty quickly, couldn't we? What's cosine hyperbolic of 0?
1 minus.
It's e to the 0 plus e to the 0, right? Negative 0 is same as 0, over 2, which would be 1 plus 1. 2 over 2 is 1. So this should be 1. So this right here, if we plug in 0, we get 1 here times 20. Is going to be minus 10? So 10. So we get y is 10, right? So that would be, we're thinking that's this point right here, the lowest point. How could we confirm that it's the lowest point? Maybe we pick one to the side and see if we go higher, right? So let's just pick something a little bigger than 0. How about 1? All we need to do is just try and convince ourselves that it's bigger than 10. And at least we know that, we're not sure it's the lowest point, but we're pretty confident that it is. X is 1, plug that in. Well, then you'd need a calculator, wouldn't you?
Right.
Okay, but without doing it greater than 10. What's another way, just for the sake of thinking here, what's another way I could show you that the lowest point on this thing is happening at 0? Think Cal 1.
Second derivative?
You could use like a second derivative test, right? You could figure out, you can find lowest points on functions, can't you? I mean, you took Cal 1, so you can find minimums of functions. So we'll do that, but it's going to require the derivative, isn't it? And isn't the slope of this line, this red line, isn't the slope of that line actually connected to the derivative anyway?
Yeah.
So let's just take the derivative of this function. After we do that, we'll verify that this is the lowest point, and then we'll actually try and figure out where that's what's happening there, where the slope is. So let's get the derivative. What is the derivative? Well, the 20 is coming with us, right? Okay, 20. Derivative of cosine hyperbolic? Just sine hyperbolic. No change in the sign, right? No change in the positive, negative, or anything like that. And then of what's in here, don't forget chain rule, derivative of what's in there. That's the same as 1 over 20x, right? What's the derivative of 1 over 20x? 1 over 20? Are we done with this part? Yes?
Yeah.
Derivative of negative 10 is 0. We don't have to worry about it. The 20s cancel. Reduce, I should say. That's the derivative, right? That's the slope of the tangent line. Now, let's see if we can convince ourselves quickly that the slope of the tangent line is 0 at 0. Can we check it? Okay, so I'm asking myself this question real quick. Where is y prime equal to 0, right? I'm hoping that it's what? I hope it's x is 0, because then my assumption that this was centered at the origin would be correct, wouldn't it? All right, so let's take sine hyperbolic of x over 20 and let it set it equal to 0. Should we just check x is 0? Just plug 0 in and see if it works? All right, let's just check it. Let x be 0. And we get sine hyperbolic of 0 over 20 is still 0. Is that 0? That's my question. Is it 0? Yes. Right, because it's e to the 0 minus e to the 0 over 2. And this time, because of subtraction, you get 1 minus 1 is 0. So it checks. So I feel pretty confident that the lowest point on the catenary was going to be at the origin. Now, why is that vital to us now, that we have that? I think I've kind of danced around this. I'm probably confused some of you here. What is it that I'm going to be looking at on this picture? Pole, wire. If I'm trying to find the slope of that line, how am I going to do it? And this is 0. What's that?
You restricted a part of it from 0 to...
I'm not sure I understand. Restrict.
Like you just basically cut it in half, now you can just work with what...
Okay, so just work with that side? Okay, that's exactly what I'll do. I'll forget the left side. Just try and figure out the slope of that line. How are you going to find the slope of that line? Okay. Yes? But do you know anything on the triangle? Hmm? You know it's 10 meters this way, yes. My height of what? Did I give you that the height was 20? I don't think I gave you the height was 20. Yeah. I think y'all are making this a little harder than it has to be. Let me ask you a different question. Let's say you have this parabola, x squared. And I go out here to 1, and I ask you to tell me what the slope of the tangent line there is. What would you do? You would take the derivative, and you would plug in 1, wouldn't you? To find the slope of that red line, all you have to do is take the derivative and plug in 10. And we're there. Yes? That's it. So that's what we're going to do. We already took the derivative, plug in 10, and we're done. The reason why I was doing all this other stuff was because how do we know that this was 10? How do we know that this was 10? We had to assume that this was 0, and the 0 was the bottom of the catenary. We didn't know that. So it could have been offset, and so we had to confirm that, and that's why I did it. You don't have to do that on your homework. Just assume it's centered at the origin. In fact, they draw the picture centered for you. They even draw the y-axis, and they show you, okay? But without that knowledge, you can't assume that that's 10. All right, so what was my derivative? Sine hyperbolic. X over 20, and I'm going to be plugging in 10. So it's a half, and I'm just trying to figure out what this is. So this is going to be e to the half minus e to the negative half over 2. Whatever that number is the slope of the tangent line, right? So I'm going to need a calculator for that. I'm using my phone as a calculator. I apologize, but It's one less thing I have to bring with me. So I'm getting 1.648 minus 0.606. It's actually 607. And then over 2. Anyone else getting this? Yeah, we'll check our final answers, right? 0.521, close enough, good. All right, so you should get 0.521. I'm feeling good about that because it's a positive number, which means it's a positive slope, and that wire should be at a positive, right? All right, so that's the angle, isn't it? No? Is that the angle? No, that's the slope of the line. And so that is not the angle. So now we have to somehow convert that over to an angle. So what I'd like to do is I'd like to kind of zoom in on this little piece right there. Just kind of zoom in and take a look at it, all right? Do that right here. Here's your pole. Here's the wire coming in, right? And what we're looking at is what's happening right there at the point of connection. And there's a tangent line that's running there, right? But the further away the line goes, we start moving away from the wire, right? And what we want to know here is what's this angle? What we do know is that the slope of this line is 0.521. So I'm going to create a right triangle now, right there. And I know that if this is slope represents what? Rise over run, isn't it? Rise over run. I'm going to rewrite this right here as rise over run. Just put it over 1, right? That means that the run of this triangle is 1, and the rise of the triangle is 0.521. Y'all with me? I think I went off my picture. That's 0.521 right here. And I want to know about this angle. I'll call it theta. How are you going to get theta? Opposite over adjacent, right? I know that tangent of that angle is opposite. Which is the opposite here? The 1 over 0.521. Arctan both sides, and you're there. Theta equals arctangent of 1 over 0.521. Now your answer is going to be either in radians or degrees, depending on your calculator. So let's do it for both. Anybody get 1.09 radians? Yeah. How do you go from radians to degrees? Multiply by 180, divide by pi. So times 180, divide by pi, 62.5. 62.48 degrees. The angle that it makes with the pole is 62.48 degrees. Now, the value of something like that, like why you'd want to know that angle, would be the thing I always talk about is, you know, these cables usually carry power, right? This was a telephone cable, but you know, these utility poles that have, you know, high-powered lines on them. And all those high-powered lines have insulators, right? You've seen these? I don't know if y'all paid attention to these. Sometimes I just assume everyone has paid attention to this, but if you connect an electric line to a pole, it's going to go right through the pole to the ground, right? So what do they put up there on the poles? Yes, but that doesn't keep it from coming to the ground. There's something else up there, right? They've got, next time you're out, take a look at it. They have these, it's a terrible drawing. Oh my God, that's horrible.
Oh, yeah.
It's a ceramic, it's usually gray. It's a ceramic sleeve or something. And what it does is so here's the connection to the pole. Here's a ceramic sleeve. Here's another connection. And this is where the wire actually hangs from.
Yeah.
Okay? It hangs from this ceramic thing. And then when it gets to the pole, there's another ceramic thing like this. And they'll connect from, I should do the electricity in a different color. Here we go. So here's your electricity coming in. It'll jumper over like this. And on the other side, there will be another ceramic sleeve like this. And it'll jumper from here to here. So the electricity cannot pass through the ceramic part because it's non-conductive, so the electricity doesn't come down the pole. If that wasn't there, then it would be an instant ground and that would be it, right? There'd be no point in having it. So you don't want these to fail, right? And they have to be able to hold the line up, and you know, lines, they're heavy, right? There's a lot of load on those ceramic insulators, right? And they're made of ceramic, so they're brittle, and you know, there's things that have to be thought about. You don't want to have too much of a load on this. So the things that an engineer would want to know are, well, how much force is pulling on that ceramic insulator, right? How much force is there? Well, to determine the force, you're going to need to know the direction that the force is coming in, right? Aren't you? I'm out of colors, but you need to know which direction that force is pulling. And that would be what we just found, right? That would tell you the angle. And so that would be useful to an engineer to make sure that they have the right size ceramic insulator for the job. Okay. You know what your homework is, yes? Any questions? We should probably try and do a quiz next week at some point, right? Do we have quizzes? We do, right? I have to check our syllabus, I forgot. I think we do have quizzes. Just be ready. I think our first quiz should be just a quiz over the homework. Just a problem out of the homework or something similar to it. So have a good weekend. Go Patriots or what? No? Go Steelers. Are they gone? I thought they were gone. Okay.